So let us discuss about analog multipliers. Basically, the analog multiplier IC number is AD633. So followed by this video, we are going to discuss about the applications of analog multipliers. So this multiplier will produce as output V0, which is proportional to the product of the two input Vx and Vy. So we can write it as V0 is equal to K times Vx into Vy. So where K is nothing but the scaling factor that is usually measured in terms of 1 by 10 volt power minus 1. So there are various methods available for performing the analog multiplications. 4 such methods are logarithmic summing technique, pulse height or width modulation technique, and next one is variable transconductance techniques, and multiplication using Hilbert cell, and multiplication using variable transconductance techniques. So if you see actually the multiplier output, I can write it as the actual output is V0 is equal to Vx plus 5x into Vy plus 5y divide by 10 into 1 plus epsilon plus 5 naught, where here this epsilon defined error signal associated with K. Okay, and this 5 naught represent offset voltage of V0. Okay, and the 5x and 5y represent the offset associated with Vx and Vy. Okay, so let us discuss about the common technology, common terms which is associated with linear analog multiplier. So first one is accuracy. So it specifies the deviation of the actual output from the ideal output. So for example, for any combination of x and y input falling within the permissible operating range of the multiplier. So next one is linearity. It defines the accuracy of the multiplier. So if you see the figure, this one, so this will shows the response of the output function for one input, where Vy is considered as a constant here. Okay, so it represents the maximum percentage deviation from the ideal straight line. So this is my ideal straight line, and so how much it get varied. So this represent the my error. Okay, so the error surface is formed by plotting the output for the different combination of the x and y input. So the linearity error can be defined as a maximum absolute deviation of the error surface. So this linearity error will impose as a lower limit on the multiplier accuracy. So next one is square mode accuracy. So the square law curve is obtained with both x and y input, which is connected together and applied with the same input signal. The maximum deviation of the output signal from the ideal square, that is from the ideal square law curve, which will expresses the square mode accuracy. So this is the deviation, right? Okay, this output I will get whenever both the inputs are same. So this is my ideal square curve, and this is my ideal square curve, and this represent the error. Okay. So now let us discuss about the bandwidth. So the bandwidth indicates the operating capability of an analog multiplier at higher frequency values. Small signal 3 dB bandwidth, which will define the frequency f naught at which the output reduces by 3 dB from its lower frequency value for a constant input voltage. This is identified individually for the value of x and y input signal normally. Okay. The transconductance bandwidth, which will represent the frequency at which the transconductance of the multiplier drops by 3 dB of its lower frequency. So this characteristics defines the application frequency ranges when used for the phase detections or AM detection. So the next one is quadrant. So the quadrant will define the applicability of the circuit for bipolar signals at its input. So the first quadrant device accepts only the positive input signal. The two quadrant will accept the one bipolar signal and one unipolar signal, and the fourth quadrant will accept the two bipolar signals. So first let us discuss about the logarithmic summing technique. So in this technique we use relations called ln Vx plus ln Vy, that is equal to ln Vx plus Vx into Vy, right? So in order to get the ln x, I am going to give the Vx as input to the ln. So you will get ln Vx and this is ln Va. So both get added. So you will get ln Vx into Vy. So if I give it to a anti-logarithmic converter, that is ln inverse, it will produces the output voltage of the summer, that is Vx and V pi. Okay. So the exponential relationship between the collector current and the base to the emitter voltage of the bipolar transistor during its active mode of operation could be explained for the logarithmic and anti-logarithmic conversions. So the relation between the I naught and Vb of the transistor, which is given by Ic is equal to I naught into e power Vb divided by n times Vt. So here the n represent 1. So it is found that the transistor follow the relationship very accurately for the range of 10 nanoampere to 100 milliampere. Okay. So the logarithmic multiplier has low accuracy and high temperature instability. So this method is applicable only to the positive values of Vx and Vy. So therefore this type of multiplier is restricted only to the one quadrant operation. Okay. So the next one is pulse height with modulation technique. So in this method, the pulse width of the pulse train is made proportional to one of the input signal, and the pulse amplitude is made proportional to second input voltage. That is Vx is equal to Kx into A. So A represents the amplitude of the signal, and Vy K y into T. So this T represent this is input voltage and this is a pulse amplitude. Okay. So I can write this Vz is equal to Kz into T, where this Kx, Ky and Kz are the scaling factor. Okay. So if you see here in the diagram, A represents the amplitude, right, and the T represent the pulse width. Okay. And the capital T represent the area of the pulse. So I can write this Vx is equal to Vz is equal to Kz into T, and T is nothing but the area of the pulse, that is nothing but A into T, right. So from this equation I can write A is equal to Vx by Kx and T is equal to Vy by Ky. Okay. So this modulation pulse train is passed through an integrator circuit. Therefore, the input of the integrator is proportional to the area of the pulse, which in turn it is proportional to the product of the signal. So this I am writing it here. Okay, so V z is equal to k z into a into t, and we know that k z a values vx by kx, and t is nothing but vy by ky. So you can see I am getting the product of these two inputs. Okay. So next I am going to discuss about multiplication using emitter coupled transistor pair. So which we have already discussed in another video. So you can refer that one. So thank you for your patient listening.